In this last lesson, we're going to learn about smart pointers and the rule of zero. So, we've learned in the last few lessons quite a bit of complicated stuff. We learned the rule of three, move semantics, the rule of five, RAII, how to manage memory resources on the free store, and admittedly, knowing how to implement all of these different functions is quite a bit. It's a lot of work. There's a lot of things to remember. It takes a lot of practice before you get these right. Okay. In fact, very often you have to look up what the implementation is supposed to be just to make sure you get it right. All right. So it's not something that a lot of people just remember off the top of their mind. The other thing is it's extremely useful to have this type of object. So a smart pointer is not something we just invented. It's actually this concept of a pointer that knows how to manage a raw pointer correctly when it comes to using the free store has been around for quite some time. And it's such a useful concept that, like so many other useful concepts, it's actually implemented already in the standard library. So this class that we've developed, we don't actually need it. We can just go ahead and use one of the smart pointers that are provided by the standard library. Now, the smart pointer we implemented is not exactly the same as the smart pointers in the standard library. The smart pointers in the standard library have additional optimizations and also additional constraints based on what you need them for. Okay, so they do things a little bit differently, but in general, they have the same overall goal of managing a memory resource. All right, so we're going to go ahead and look at unique pointer first. Unique pointer is the most common, and 90% of the time this is the type of smart pointer you should be using. Okay, so here again is our code which works on some sort of image, process image, right? So we were using this big object that we don't want to keep on the runtime stack. And so this is how to use it with a unique pointer. So just like we had used the smart pointer of type image as a generic template class and used it with type image, you'll notice here that we're using the unique pointer. Okay, so look at the data type of image pointer A. It's of type standard unique pointer of image. In order to get access to the smart pointers from the standard library, you have to include memory. Okay, the way that you create a unique pointer is you use this special function called makeUnique. And it's an interesting function because what it does is it creates a unique pointer, but the arguments to this function are the arguments to the constructor of the object you're trying to construct. So I know it's maybe a little bit strange, but we construct an image object with a string, just one string. So the arguments to the makeUnique function is just one string. It's going to go ahead and forward those arguments to the constructor of the image class when it calls new and creates that object on the heap. And what it returns is a unique pointer. You can see here, unique pointer of type image. That's what gets returned from this function. Okay, so I'm creating 3 images on the heap using makeUnique, which means that I have 3 unique pointers to those objects on the heap. These objects are not on the runtime stack, they are in the free store. And I'm calling process image and using standard move to move the unique pointer into that function, and then I'm also doing a copy, again using standard move. Now, and if we run this code, we will see that everything works just fine. Okay, so this will validate that unique pointer is indeed a viable replacement for the smart pointer we had developed. So here we go, we're creating 3 images and then we're destroying 3 images. And even though we have a copy and a assignment, there's no extra copies of those images. Okay, we're only making shallow copies because we're using the move semantics that we learned about. Now here's the thing you need to know about unique pointers, okay? unlike the smart pointer we've developed, the unique pointer deletes the copy constructor and the copy assignment operator. Okay. What that means is that it completely removes these functions so that they cannot be used. So you cannot copy construct a unique pointer and you cannot copy assign a unique pointer. Let me show you what I mean. If I try to just be inefficient and pass unique pointer by value into this process image function, this would make a copy of the unique pointer, right? This code doesn't compile, okay, and it's kind of a complex looking error message, but what it's saying is that unique pointer being constructed from a const unique pointer reference, right? That's the copy constructor signature, cannot be referenced. It is a deleted function. Likewise, when I try to assign from unique pointer C into B, I get the same kind of error message. The operator equals, where I take a const unique pointer reference to the other type, is a deleted function. Okay, so the copy constructor and copy assignment operator have been deleted. So when I use unique pointers, if I ever want to copy or assign them, I actually have to copy construct or, sorry, move construct or move assign them. Okay, why do you think they do this? So the reason that unique pointers require move semantics is because it's in the name. Unique pointer enforces only one owner of an object at a time. Okay, so it's basically like it's a special type of smart pointer that you only use in the most optimal case. You only use it with move semantics. It's just completely removed the copy semantics. You shouldn't be making deep copies at all ever. So the copy constructor, copy assignment operator, like I said, have been deleted. You cannot invoke them. All right, so it forces you to use them only in the optimal case. And by doing that, it also has the benefit of preventing you from ever having more than one owner of a specific memory resource. All right, so most of the time, that's exactly what you want. You want a unique pointer, and that's fine. There is another pretty common type of smart pointer called a shared pointer. A shared pointer definitely has its uses, but it does things completely differently. It also it also doesn't make copies of the underlying data. Okay, so it's optimally efficient. But it allows for multiple shared pointers to refer to the same underlying object, and the way that it does that is it uses a reference count. So every time you copy construct or copy assign a shared pointer, it's going to increment that reference count, and every time you delete or destruct a shared pointer, it's going to decrement that reference count. And the last shared pointer left, when it goes out of scope and gets deleted, and that reference count goes below 0, that's when the object is actually deleted from memory. Okay, so shared pointer is very similar to unique pointer and how you create them. So there's a special function called make shared. So if I want to make a shared pointer instead of a unique pointer, I'm going to go ahead and do that. So now image pointer A, B, and C are all going to be shared pointers to images. And I'll just point out that if I use shared pointers, I don't have to use the move semantics because everything will work just fine. This also needs to be a shared pointer. Okay. And if I run this code, you will see that I still get optimal results. I'm not making any copies of those images at all. Okay. But the approach is slightly different. So When do you want to use a unique pointer as opposed to a shared pointer? You use a shared pointer whenever it makes sense logically to have multiple owners of that memory resource. Okay, so maybe you have a program where you're keeping track of the same data from more than one location, like maybe you have a few different data structures which are all referring to the same data. In that case, you might use shared pointers. Most of the time, maybe even like 99% of the time, honestly, most of the time, all you need is a unique pointer. It's actually pretty rare to need the shared ownership semantics of a shared pointer. So most of the time, all you need is a unique pointer, and you'll get by just fine with that. So this leads us to the rule of 0. You saw how complicated it was to implement this smart pointer correctly. There was just a lot of stuff that we had to do and get right to get everything working correctly with the rule of 3 and then the rule of 5. It was pretty painful. However, the standard library provides you with generic classes which do exactly what you need in most cases. So if you are managing a memory resource, just use the smart pointers from the standard library. If you're managing a file system resource, just use the file management from the standard library. If you're using a dynamic string or array, just use standard string or standard vector from the standard library. So the point is, you should never have to actually do all of this work, when you're writing real code because it's already been done for you. The rule of 0 states that whenever you need to manage a resource, you should not provide a custom implementation of any of the default functions. You should not provide a custom implementation of the destructor or the copy constructor or the move constructor or the copy assignment operator or the move assignment operator. Don't do any of that. Just use a resource managing class that's provided as part of the standard library. If there's a new kind of resource that nobody's provided a resource managing class for, in that case you're going to have to apply the rule of 3 and the rule of 5, but that's a pretty rare situation to be in. So as I said, most of the time you're managing resources that somebody has already developed a proper resource managing object that properly uses RAII, resource acquisition is initialization technique, and you can just take advantage of that object. So use smart pointers. Anytime you need to put memory or put objects on the heap, just use smart pointers and you'll be good.